I'm Andy Sipocz. I'm a biologist at Texas Parks and Wildlife. I work with the state parks, not with the wildlife division. So our state parks, a lot of them were farms and ranches before becoming parks. They weren't like Yosemite or Yellowstone, so they need a lot of work to bring them back to their natural state, and that's really my job. My office is at Sheldon Lake State Park, which is where the state park's regional office is located in the northeast corner of Harris County. Northeast corner of Bellway 8 in northeast Harris County. We administer about 14 state parks out of that office. So Mission Tejas up near Nacogdoches, all the way down to Searim near the Louisiana border, and Brazos Bend State Park, Galveston, Lake Somerville up near College Station, all the parks within that region. So I'm going to talk about conservation of natural landscapes, including trees and forests and natural canopies in a rapidly changing climate. So first, what is climate change? What's going on? You have probably heard that climate of the earth, and as George said, has always been changing over time. What's going on now is two big differences. One, the rapidity of the change is amazingly fast, and the fact that it's caused by people instead of some natural phenomenon. But this is some data from the Vostok ice core out of Antarctica. Vostok is the Russian research station there. And they took an ice core, so that ice sheet in Antarctica has not melted, probably hasn't melted completely for 30 million years. It's probably been in existence for that long. And so they were able to drill a core to the bottom of the ice sheet, or near the bottom of the ice sheet. And when they pulled it up, they found that the ice at the end of the core was about 1.2 million years old. And why that's important is because as snow is falling on the ice sheet and making every year, making a new layer of snow, that snow is preserving in a sample of the atmospheric composition at that time. How much carbon dioxide and other things are in the air, how much oxygen, the temperature of the air, how humid it is, all that sort of stuff is preserved in these cores. You can even see like volcanic eruptions that occur will be a little thin layer of ash in an ice core. And then again, these cores are laid down, it was laid down over 1 million years, but you can get a very accurate reading of how old a specific piece of that 2-mile long core is. So you've got 2 miles of ice they pulled up. And it's not an annual, but it's pretty close. The ice core they pulled out of Greenland, for example, you could tell when the Romans started smelting lead because the lead showed up in the core. And there's some other really cool things like volcanic explosions that happened when we were still running around in furs and stuff. Scientists are trying to find out, well, where was this volcano that exploded? But anyway, what you see on this graph is temperature, is the top line going up and down with each. So we've had about 41, I believe, ice ages now over the last 3.5 million years. But these are just recording some from the past 400,000 years. So about every 100,000 years, the Earth will go into an ice age. This is levels of carbon dioxide, which follow the temperature graph really well. Concentration of dust, you tend to get a lot more dust during the depth of the ice age when there's very little vegetative growth, relatively less vegetative growth, and conditions are drier and windier. So that's interesting that carbon dioxide follows the 120,000 year ice age cycle so well. It's actually not changes in carbon dioxide which initiate the beginning or the end of an ice age. It's actually slight changes in the amount of sunlight energy that's reaching the Earth and what time of the year the sunlight is hitting the Earth and whether it's more concentrated in the southern and the northern hemisphere. So the Earth is constantly, it's like a top, right? It's spinning, but it's wobbling as it spins. And so it's got this long cycle, I believe it's 23,000 years, in which it makes a full circuit. And so it's some years the Earth is pointed more, the northern hemisphere is pointed more directly towards the sun, and so the northern hemisphere, which is where most of the continents are, gets more sunlight than the southern hemisphere, and because of the concentration land masses, it heats the Earth up a little more. At any rate, there's a number of overlapping cycles. It's how round or how spherical or how elliptical the Earth's orbit is. Whether the Earth is closest to the sun during the northern hemisphere winter or furthest away from the sun during the northern hemisphere winter. All those come together every now and then to form this regular series of ice ages the Earth goes into. So right now, according to this cycle, we should be slowly descending into another ice age, which of course we're not. What carbon dioxide does is as the amount of sunlight hitting the Earth slightly changes, say we're coming out of an ice age, the Earth starts to heat up a little bit, and as the Earth heats up, the oceans heat up, they can hold less carbon dioxide dissolved within them, so they start degassing carbon dioxide. Plant growth, more decay starts to occur because the Earth is warmer. Again, you have more release of carbon dioxide, and this is like, it's a positive feedback. So as more CO2 goes into the air and the Earth starts warming a little more from the increased sunlight in the northern hemisphere, water vapor increases. Warmer air can hold more water vapor. All these things act as a positive feedback loop, and then bam, we pop out of the ice age relatively quickly within about 12,000 years or so. And then once again, the cycle goes in the other way, in which northern hemisphere slowly starts getting a little bit less sunlight. The ice cap on Greenland starts to grow. It reflects more sunlight into space because you've got more of a white covering. And so you have these negative feedbacks, and so the Earth plops back down into another ice age. So what's happening now? Carbon dioxide is it's the ultimate control, thermostatic control of the Earth. And as humans are tweaking it, we have not only popped out of the ice age, but we're going to a much higher temperature, one that hasn't been experienced for 50 million years. Looking on a much larger scale, this is 400 million years ago, when there wasn't much life on Earth that we would recognize, except maybe some bony fishes, I think, started about 400 million years ago, maybe, right? You can see the CO2 started declining, has been declining over a long period of time, and then a really important thing happened right here. We had quite a strong decline of carbon dioxide. What happened there was two things. One, the Antarctic ice sheet started to form because the Antarctic continent had moved. You know, the continents are all moving around on really long time scale. Antarctica moved over the South Pole, and ice started accumulating on it. And then also the rise of the Himalaya mountains. India crashed into Asia, and the Himalayas pushed up. So you had a lot of erosion of sediments going into the ocean. Those sediments tend to sequester carbon dioxide through some really complicated chemical reactions that I can't explain. But the amount of CO2 started dropping quite a bit, and that really changed life on Earth. It changed the plant communities and the animal communities that we have today. We know what past CO2 levels were from soils that have been petrified, paleosols, liverwort fossils, leaf fossils. You can look at leaves, and leaves all have little holes in them where air comes in and out, oxygen comes in, CO2 comes in, oxygen comes out, and vice versa. The size of those stomata reflect how much carbon dioxide is in the air. So when CO2 is lower, the stomata are actually larger. And you can see that in fossils of leaves. So we got a pretty good idea, a generally rough idea of what CO2 levels have been over the past 500 million years. Again, you've had the beginning of Antarctica, so CO2 dropped more with the beginning of ice ages, and then about 3.5 million years ago, the Greenland ice sheet formed, and then we started going into these regular series of ice ages. And what this graph shows is here's CO2 levels. These are the levels here that are expected to occur as we continue to burn fossil fuels. This 2,000 parts per million is like if our economy continued to grow and it was all fossil fuel based. I don't think that's going to happen because, especially countries like China are completely moving off fossil fuels relatively rapidly. But if that were to occur, we would have to have a spacesuit to go outside. So nobody, their life on Earth hasn't seen that since long before the dinosaurs even were around. If we come to RCP 6, I forget what RCP, it's like It's an acronym for a pathway that civilization can take as far as how much CO2 we're going to put into the atmosphere. But RCP6 would be loss of the Antarctic ice cap and the Greenland ice caps. You know, Missouri, Tennessee would be on the Gulf of Mexico. We'd have about 240 feet of sea level rise. Not something we would really want. RCP 4.5 is kind of where we're going, and eventually that would be loss of all coral reef in the world, which is happening. It's pretty much set in stone. That's going to happen. Massive biodiversity loss, sea level rise of about 3 feet by 2100. Possible halting of the Atlantic meridional overturning circulation, which could really play havoc in weather in Europe. And sea level rise eventually of about 40 to 80 feet. That's where that's pretty much set in stone. When I say 40 to 80 feet of sea level rise, that's going to take, 1,000 years for it to fully play out. So like we would be under about 30 or 40 feet of water here. This is just an interesting graph that just shows CO2 over time relative, here's the CO2 is this blue line, relative to the amount of energy the sun has been putting out. So if you look over the history of the Earth, over the last 5 billion years, 4.5 billion years, the sun is actually putting out more energy than it has in the past. But thank goodness, the amount of carbon dioxide in the atmosphere has slowly been decreasing, and so the two are offset, keeping the Earth at a really nice habitable temperature. Temperature of the planet Earth, this is another graph that goes back 500 million years. You can see here, temperature of the Earth dropped down. This is when the Antarctic ice cap formed. We started having a series of ice ages. This is when the Greenland ice cap formed, about right here. And since the Greenland ice cap formed, we've been in this relatively narrow temperature range, depth of the ice age, interglacial, nice warm period like we're in now. This is about where we're expected to be in the year 2100 under current scenarios, which would be about the same temperature that occurred when about 30 million years ago. So we got some really huge, massive potential changes. So what does this mean for plant communities? That's what I'm supposed to be talking about. That was just a bunch of background information. But one interesting thing is that as the amount of carbon dioxide has decreased in the atmosphere when the ice ages started with the initiation of the Antarctic ice cap, the world used to be filled with brachiodont mammals, grazing mammals. These are mammals that have teeth to chew up wood, so browsers. So at one point, we just had mammalian browsers. We did not have grazers like cows. They had not evolved yet. As the amount of carbon dioxide decreased and the Earth cooled and started to get drier, overall, grasses evolved. And once grasses evolved, we started getting animals that could chew woody material and grasses, and then finally just animals that would just eat grass. Mesodonts and hypsodonts, so this all describes the kind of tooth pattern that the animal has. So hypsodonts are ones that feed on grass. This period right here is when C4 grasses or warm season grasses evolved. And at that point, we had a really big increase in the amount of animals that are able to graze on grass, and quite a large decrease in the number that graze on woody plants, because at that point, what happened, once warm season grasses evolved, a really big change happened, which is a massive increase in the amount of fire that occurs on Earth. So warm season grasses are very well adapted to burning up. And this is well before humans were on the stage, so it wasn't just us lighting fires. And the neat thing is, this correlates really well with the amount of charcoal found in sediment cores. When you take sediment cores and off near land, you can find charcoal remnants in it. So you have a big fire, you get ash that falls out over the ocean. That's all preserved in sediment cores that can be looked at and aged. So we know that at this point there was a lot more fire on Earth just through the evolution of these warm season grasses. So when we look at Texas today, almost the entire state is a grassland. Even East Texas, where we have piney woods, the natural condition of that land is mostly pine savanna, where you have a pine overstory and an understory of warm season and some cool season grasses. Things are a lot different today, but it's not its natural condition. So we can kind of get an idea that a couple things, as CO2 increases, warm season grasses may be at a evolutionary disadvantage. When I say warm season, these are grasses that have evolved to be able to use much less carbon dioxide in their metabolic pathway than other woody plants or other grasses. So as CO2 increases, they're losing that competitive advantage. Yeah, 1,000 times increase in fire with the evolution of warm season grasses 8 million years ago. Here's some examples of recent climate change. This is North Africa. And an interesting thing in North Africa, if you go to the Sahara Desert today, there are, it's not all blowing sand. There's plenty of rock formations, caves and such. You can find fossils in those caves of animals that occur further south in Africa where it's a humid savanna. So at one point, not that long ago, 10,000, 8,000 years ago, the area where the Sahara Desert is today actually had a lot more savanna in it. Actually had savanna in it. It had lakes, it had rivers. There are fossils of giraffes and zebras and hippopotamus in areas that are just in the middle of the Sahara now. And there's rock art, petroglyphs, where people painted on these cave walls pictures of them swimming is the famous one, the Cave of the Swimmers. Also pictures of elephants and giraffes and stuff. And for a long time, archaeologists, anthropologists wondered, had these people traveled to Central Africa and brought these animals back? Maybe they traveled down there and saw them. No, when they started finding the fossils, they realized that what's the Sahara today, not that long ago, was actually savanna with rivers, lakes, marshes, swamps, and all that. Pretty cool. All that is buried beneath the sand today, and there are ground penetrating radars that can actually follow those old river courses. In the Houston area itself, we've had some pretty big climate changes as well, and although not on that kind of a scale, it has resulted in quite a bit of change in our landscape here. This is the Trinity River in Liberty County. Here's Moss Bluff. Liberty is somewhere here. But the Trinity River, this is it today, and it's this little thin, skinny, wiggly thing. You can tell the size of a river, how much flow is in it. George mentioned this by how tight the curves are in the river and how wide the channel is. This is an old channel of the Trinity. Notice how huge this arc of the curve is and how wide this channel is. That channel is about 1,200 feet wide versus today's river, which is about 200, 250 feet wide. So at one time during a past climate, this actually was about 30,000 years ago, the Trinity River carried 9 times as much water as it does today. We had a much, much wetter Texas during the Ice Age than we do today. The dominant tree in East Texas was spruce and fir, not pine. More recent climate change, this is the results of pollen core, a sediment core taken out of Arano Bog. Arano Bog is a small pond located off Spring Creek at the north side of Harris County. And they took a sediment core down to the bottom of it, and inside that sediment preserve, because this pond doesn't dry out, so there's no oxygen in the sediments below the water, and anything in there does not decay. And so they're able to find actual pollen grains, and they could tell at what point in time that pollen was deposited. The further down you go, the older it is, and up near the top it's present day. And what they found is in northwest Harris County, kind of maybe just north of where we are today, the forest was dominated by pine trees. So it looked like East Texas does today. And as time went on over the last 2,000 years, so not a really long period, this climate here has actually warmed up and dried out relatively. And so we have a lot more herb pollen and a lot less tree pollen. So if you go towards Katy, what is now prairie and oak savanna, post-oak savanna, that used to be pine forest just 2,000 years ago. With the amount of climate change we've already had, we can expect some really big changes in our plant community. And I'm going to show you some examples of how that's going to occur. The area here has not caught up to its present climate, but it's working that way. This is from Maryland, Delaware area. We're using LIDAR, which is, do y'all know what LIDAR is? You can measure topography, elevations really accurately by flying a plane over the land and sending down trillions of laser beams. And depending on how long it takes for that light to get back to the receiver in the airplane, tells you how high the land is, which is amazing that a computer is that fast that just, a beam of light that's going the speed of light, and there's a difference in how long it takes to get back to an airplane. And they know, the plane knows where it is through GPS. And this could be accurate to within a couple centimeters. But the neat thing is it doesn't penetrate through like leaf canopy, but if you look down, if you're above a forest looking down, there are tiny little places you can actually look all the way and see the ground. And because the plane is emitting so many billions or trillions of these laser beams, it does find that true floor, and it has allowed us to actually see that throughout the northeastern coastal plain, there are sand dunes that are now covered in forest. It's like how down in the Yucatan, they're finding all these ancient Mayan temples that have been covered by trees and had no idea they were there. That's all through LIDAR. So we're finding that during the Holocene optimum, about 8,000 years ago, when all of those solar factors came into alignment and produced the hottest natural climate we were going to have before we started dipping back into the next ice age, there's some really cool things that happen to our plant communities. And the neat thing is this tells us where we're going to be heading now with climate change. It gives us an idea, okay, this happened in the past during a natural warm period. We're now in another warm period, not natural, but we're going to have an idea of what is going to happen to our world. Oh, here's another example. Mima Mounds at Brazos Bend State Park. This is after a fire, a prescribed burn in the prairie at the park. Brazos Bend is just south of here along the river. You have these little mounds of sand. Those are sand dunes, and those are from a past climactic period when things were drier. And say you had a fire, the soil would be denuded. The sand could blow around and form these little dunes. These are found all through the coastal plain of Texas. And if you go down towards South Texas, this is from the Powderhorn Ranch on Matagorda Bay, where the climate is naturally drier than it is here in Houston. These same dune forming processes are actually occurring. You can actually see them happen. This is just expected temperature increase with climate change, 2080, 2099, the number of days over 90 degrees. So in the Houston area, they're expecting that about half of our year, between 165 and 180 days, will be over 90 degrees. Changes in soil moisture projected. So Texas, you can see a slight drying in soil moisture. This is actually a lot worse than it appears because that's seasonal drying of soil moisture. It actually is expected to increase in the winter and then be less than it is today in the summer. Overall average is slight decrease, but seasonal decreases are quite massive. And soil moisture is really one of the main things that controls our plant communities. So if we have a decrease in soil moisture, we can expect plants that are more drought resistant to begin to dominate. Changes in evapotranspiration, again, the Houston area is about even, really not much change, but that's an annual average. We actually have quite a bit more evapotranspiration in the summer and less in the winter because our winters are going to become wetter than they are today. Our summers are going to be hotter and drier. Winters will be warmer and wetter. Summers will be warmer and drier. Do y'all know what evapotranspiration is? It's a combination of evaporation from the soil of water and the amount of water that plants are pulling out of the soil, transpiration. So the hotter and drier it is, the more water plants will try to at least pull out of the soil if it's available. So what's going on here? Well, here's Bastrop State Park after the fires in 2011. Most of the pine forest was burnt up. And what survived were the native grasses and post oak trees. And so Bastrop, is the hidden pines, right? It's an area, if you go west, you're out on the prairie and suddenly you come to this beautiful pine forest. It's there because the soil conditions are really favorable for tree growth. They're nice, deep, loamy soils. When it rains, that water soaks right into the earth where it's stored and it's available for tree growth. Trees do not like drought. Grasses, they laugh at drought for the most part. They laugh at drought, they laugh at fire. So this hotter, drier, more fire-prone climate we're going into is going to be much more favorable for grasses than it will be for trees. So at Bastrop State Park, this is an example of what we're going to see more and more of in Texas. The forest areas that we're used to seeing are going to be displaced one way or another, whether catastrophically like in Bastrop or it's just going to happen overnight like it has here in Houston. This is the Herman Brown Park. If you go on Highway 90 north, like you're going towards Liberty out of Houston, Highway 90 is kind of north, runs parallel but a little north of I-10. Herman Brown Park, you drive right through it, and during the 2011 drought, the pine trees just died. There was no disease. I mean, there was some disease because the trees were weak and sick, but that wasn't what caused the massive mortality. There wasn't any fire. It was just it did not rain for such a long period. The pines died. The post oaks, which you see here is the green, they survived. And so you see a direct example from a climate-induced change from pine to an oak-dominated forest. This also happened at the Houston Arboretum in Memorial Park. I went out to take a look at it with the folks out there, and I said, look, all these pine trees that died are the ones that are on the clay flats. Very bad soil conditions for pine trees. They probably didn't belong there to begin with. The ones that survived were on these Mima mounds, nice sandy mounds that had good loam soils. So what they've done is, rather than replanting the whole area with pine trees, they removed the dead trees and they planted those clay soils with prairie grasses. So now you've got a pine savanna there. And they've actually conducted a couple prescribed fires inside the 610 loop. That's pretty neat. So how do we conserve native plant communities? What options do we have? Well, first of all, as I've indicated, the climate has been naturally changing for many millions of years. And plants are adapted to that somewhat in that they can move over time. They have dispersal mechanisms. So when in Texas, just like the hidden pines were a remnant because of good soil conditions of a wetter, cooler climate, we have examples of that all through the state. This is a Davis Hill State Park where we have these deep, it's a salt dome that's pushed up a cap rock of sandstone right off the Trinity River. It's really neat. You're on this sandstone bare rock and you're about 250 feet above the bald cypress swamps along the river. It's a really cool place. And it's got examples of really wet, humid environments where you have things like ferns and orchids, rare orchids growing. And then on the sandstone, you've got this where trees can't grow because there's like no soil. It's just open prairie. There are plant communities all through this part of the state that are relics of either wetter or drier periods of time in the past. And if we can conserve those areas, we can conserve all the building blocks that are going to be needed to reassemble new plant communities as the climate changes and then hopefully at some point stabilizes. Like Aldo Leopold said, the first rule of intelligent tinkering is to save all the parts. So let's save all the parts so that when we're all said and done and have regained our sanity, we can kind of reassemble natural systems that operate on their own and preserve biodiversity. That's probably the best way of achieving that. This is another picture of Davis Hill. Again, Davis Hill State Natural Area. It's right off the Trinity River in Liberty County. It has the greatest number of different kinds of plant communities of any state park. This is me. I wanted to compare myself, but this is a picture from early 1900s taken by an ornithologist. He's right here. He's wearing the gloves and he's got his vest on and his tie. And here's the guy in the stovepipe hat and the boots with the gun. So the ornithologists back then would walk around with their gloves and somebody else would shoot the birds and then they would study them, But I just like the surly look on their faces. So whenever somebody takes a picture of me up against a tree, I try to imitate that surly look. I don't know if I've succeeded or not. This is Dick Benoit Prairie Park. You can see that it's now surrounded by development, or almost completely surrounded by development. This is an area that was set aside to conserve prairie and these natural ponds that we have embedded throughout our coastal prairie. That's Dr. John Jacob in there. Maintaining and replacing natural processes with management actions. A lot of our plant communities, fire was a way in which they're adapted to fire. They need fire in order to survive. And we've taken fire out of the picture through our suppression methods for the most part. We still have catastrophic fire. But we don't have the normal regular fire that used to occur in our grasslands every few years. And so replacing those natural processes that urbanization and agricultural development no longer allowed to occur is a way of preserving plant communities. It's a way of saving all the parts. This is an example of a little blue stem prairie, again, at Davis Hill State Park that's being taken over by yaupon shrubs because of lack of fire. And again, you see these trees, they should not be here. You've got Indian plantain, which is a open prairie plant that's somehow surviving in the understory for a little while at least in the shade. Again, because lack of fire has allowed the forest to grow up in what was prairie. This is Huntsville State Park. And again, it's an area we do a lot of prescribed fire in. You walk around, you think it's all pine forest, you know, it's always been pine forest, it's just nothing but needles in the understory. But when you look closely, you see that a lot of the pine canopy is shortleaf pine. That's a tree that requires fire in order to grow and survive. If you don't have fire, you don't have shortleaf pine, you have loblolly instead. Shortleaf, unlike most pine trees, if you burn it, it will actually sprout from the roots. Like typically you cut a pine tree off, it's done, it's dead. A shortleaf will actually sprout. And if it gets burnt up, it'll send shoots out from the trunk. Coral bean, I found that out at Huntsville, which is a beautiful little prairie plant with the red flowers. Spiderwort I found, little blue stem I found in the woods, yucca and cactus are in the woods. They're just in this pine forest that's dying to be burned. Open it back up and make it into a savanna rather than a closed canopy forest. This is at Galveston Island State Park, and this, again, we burn it. It's like black charcoal, and then within a couple weeks, it's all green and flowering. These plant communities need fire just as much as they need rainfall. This is a graph I thought was really cool that shows the frequency of fire here in Texas, or actually in the central United States. A guy out of Arkansas, he's actually retired and is living in Tyler, Texas now. But back when Native Americans lived in the state, they used to do a lot of prescribed fire. They used to set fire quite a bit because it's good for animal habitat. It makes walking through the forest a lot easier. When people first started coming into the area, most of the Native Americans were displaced, and so fire came to a halt or they died of disease. Early settlement of Texas, the early settlers burned the heck out of the place for cattle grazing. And then Smokey Bear came along, and now we're at this really bad point where we don't have much fire on the landscape. And a lot of our plant communities in East Texas are really suffering. So again, prescribed fire is probably the #1 management tool that we use in state parks to maintain native plant communities. Assisted migration. So during the last ice age, we had, like Indiana was under a mile or more of ice. Okay, well now when you go to northern Indiana, it's this beautiful forest. The trees, after the ice left, the trees came up from their southern refugia and very quickly, relatively quickly, colonized the northern U.S. So we know that forest systems and other plant ecosystems, we know they can move north, south. It does take time though. It's probably 6,000 years for trees that were, during the Ice Age, were stuck along the Gulf Coast. And after the end of the Ice Age, they moved up, as far up into Canada. That probably took about 6,000 years for that to occur. So right now, we're doing the same amount of climate change in, a decade that had occurred then in about a millennia. Trees have very long generation times. So you may have a tree that could live hundreds of years. That tree can survive in a different climate than what it first sprouted up in, but it may not be able to reproduce in that climate. The seedlings are much more, they're not as resilient to climate conditions as the adults are. The adults have these big established root systems, the seedlings don't. So we may have a forest that 50 years from now looks kind of the same as it does today if it doesn't get burnt up or something. And we're like, well, scientists say it's like 2 degrees warmer, but you know, we have the same climate that Brownsville does. Why don't we have the same forest that Brownsville does? Well, because these adult trees aren't just going to, oftentimes they're just going to hang on, right? But they're not going to be reproducing. They're not going to be making acorns or whatever they need to have. Bald cypress is an example. Bald cypress most assuredly will not be able to survive and reproduce in Texas probably within 50 years. That's a shame because it's one of my favorite trees. But one idea is that we can assist our plant communities in their migration. We have a number of conservation areas, right? But they're separated by large areas of agriculture or urbanity, and trees aren't going to be able to move north on their own. So what scientists are talking about doing is actually assisting them by gathering seeds and planting them into new areas that are further north. The Nature Conservancy is doing this in Appalachia. Up on the Cumberland Plateau, they're actually taking, it's the same species of trees, but you think about a white oak that's living in East Texas, and you've got a white oak that's living in Maine. It's the same species, but the genetics are quite different. So what they're doing is they're taking oak acorns from a tree that's growing in the southern Appalachia, and they're moving it to the northern Appalachia and seeing if it does better up there than the existing trees. And if it does, they're going to start doing this whole scale with all kinds of plants. It sounds crazy that our natural world is going to be completely dependent on humans, but that's just the way it's going to be. Again, you can grade my surly look. I think this one's really up there. Another thing we can do in the face of climate change is just let change happen. So when the pine forest gets burnt up at Bastrop, we did not immediately go in and plant the whole park with pine trees. We did plant some of it back with pine because everybody, the Boy Scouts made us do it. But most of it is post oak savanna. It's coming back as beautiful post oak savanna. We're just going to let it be post oak savanna. A couple flies in the ointment as far as recreating and restoring and maintaining native plant communities. One is that plant communities are really sticky. I've kind of already hit on this point that if you look at coastal prairie, it occurs from Mexico to Louisiana, right, to the mills to the Mississippi River. Coastal prairie in Louisiana can get 65 inches of rain a year. Coastal prairie north of Brownsville may get 25 inches of rain a year. So what's creating that ecosystem? Well, the plants do vary from one end to the other, but mostly what you're looking at is an ecosystem that's created by predominance of clay soils, gumbo clays, and fire. So plant communities are not just affected by climate, they're also affected by soil conditions. So if you've got a plant community that needs this clay soil here to exist, it can't just like move to the next piece of clay that's not there, you know. What are we going to do about that? Well, what's going to happen is the generation of completely new, novel plant communities is going to occur. The plant communities that ecologists are familiar with today may not exist in the future. The species of plants may still be there, but not in the same combination that they occur today. Another fly in the ointment is we're actually losing a lot of ground to sea level rise. Galveston Island State Park, since it's become a park, the beach has moved in about 500 feet. It was established in 1972. Just during Hurricane Ike alone, we permanently lost 38 acres of land to the Gulf. That's going to be greatly exacerbated in the future. This is the tide gauge reading from Galveston. Pier 21, that gauge has been in place since the late 1800s. And since that time, we've gotten 2.1 feet of sea level rise since the gauge was established. And that is just accelerating. And if you think that's not much.
So with sea level rise, I mean, obviously there's the connection with sea level rise, forming oceans and expansion. But in that particular graph, you've got, it's from 1910, so like, it looks like it was a steady increase even before we had real things in industrialization, or do you think that's actually from the industrial?
It's actually from land changes. just cutting down forest has been heating up the earth and putting a lot of CO2 in the air. So CO2 has been going to the air a lot. But if we were to show this graph, if it extended to today, starting in the year 2000, actually curving way, way up. So this is 2.1 feet over 100 years. Since I've been with Texas Parks and Wildlife, we've had 8 inches sea level rise in my 35-year career. There is a little blip here from subsides from Texas City as well. So most of it has been actually real sea level rise. Some of it, though, is from land sinking. This is what's predicted, about 3 feet, 2 to 3 feet.
And the land sinking is we're pumping out too much in that area?
Well, the Houston, well, really a lot of coastal areas throughout the world, pumping out groundwater. It's like putting a hole in a waterbed. It deflates, and so the ground sinks, and so the ocean, doesn't sink. So the land gets covered. When I first started here with TPWD, my boss said, "Here, I want to show you something cool." We got in a boat, and he took me to the Brownwood subdivision in Baytown, which had sunk 10 feet from subsidence. And I was on a high tide, and we could have taken the boat right through a picture window into somebody's living room. The house was abandoned, of course, and there was no glass in the window. But it was just incredible, how quickly that occurred. But that was subsidence. But yeah, subsidence, there's been 12 feet of subsidence in places of Houston. We've lost over 30,000 acres of coastal marsh just in Galveston Bay from subsidence.
Are there other causes for subsidence other than pumping, or mostly just pumping?
It's all from fluid and gas withdrawal. So it could be, most of the Houston subsidence is from Exxon Baytown. They pretty much did the whole dang thing, almost. Amoco in Texas City, same thing. People knew we're going to lose all this real estate. If they knew how expensive real estate in Houston was going to be, they might have chosen something different, but they did not want to bite the hand that fed them. So they eventually went on to surface water, but there still is subsidence. Oil and gas withdrawal. This is what happens to barrier islands as they face sea level rise, as they try to migrate inland. Storms will push the sand behind the island, and the beach will just keep moving up, just like you've got a slope and it just moves up. Chandelier Islands are an example of a barrier island that did not make the cut. It's just dispersing across the floor of the Gulf. There is Sabine Bank. This was just 5,000 years ago. This was a peninsula and an island. So cores that are taken out here still find peat sediments from when there were marshes behind the island. Searim State Park, we found mastodon teeth and all kinds of neat stuff from animals that lived out on that island back in the day. It's really cool. So is that the fate of Galveston Island, Bolivar Peninsula? I don't know, maybe. Probably at some point, anything that's not protected behind a dike is going to be gone. Brazoria National Wildlife Refuge, 60,000 acres of beautiful prairie and marsh is definitely not long for this world. So there's not some good things. One thing I wanted to emphasize was the massive loss of native plant communities in our area already, even without climate change. This is a small grove of pine trees on the prairie. This photo was taken, I think, in the late 1800s. That's what Houston used to look like. This is from the Angleton, Freeport area. And this is in Harris County, where the guy was complaining because of lack of fire, with the Native Americans gone, loblolly pine forest came up in what had been a really nice coastal prairie. So even in the late 1800s, they were complaining about tree invasion, in the prairie. I find that just interesting. This is my office from the 1950s. This is completely forested now. I like the old vehicle there. It's kind of neat. There is stuff published by the government. National Roadmap to Respond to Climate Change by the U.S. Forest Service has some good information in it. This is a prairie at the San Jacinto Monument that I helped restore. That used to be a Chinese talo forest. So there is a lot of good conservation work we can do. This is just a map of Pilant Lake at Brazos Bend State Park. It's over 1,000 acres of swamp that had been half drained. So we went ahead and plugged the ditch up, put a water control structure in it, and actually restored this whole swamp community. It's really neat. You see the dead trees there because it had been drained since the 1800s, so a forest had taken root in it, what used to be a lake and a marsh. So we did kill some trees there, but if you see the number of waterfowl using the area now, you'd probably would agree that it's worth it. And around the edges of it, we are planting swamp trees. That's a overcup oak. This was a San Augustine turf field at Sheldon Lake State Park. We actually had 100 acres of just San Augustine grass that a tenant farmer was harvesting to plant lawns with. So Bill Neiman, Native American Seed, came out and planted that. There were marsh ponds embedded in all of our coastal prairies, so most of them were filled in by farmers. We actually dug the ponds out that used to be there and restored those as well. So this is that same pond. It's right here after restoration. And this is the same San Augustine turf field after it was planted to prairie. Doesn't look like that today because it needs to be burned. So it's got a lot of brush and small trees. That's everything.